How do macrostates define entropy? Imagine a room filled with 1,000 colorful marbles. Each arrangement of those marbles represents a different way they can be organized. This is similar to how macrostates and microstates work in thermodynamics. Entropy is a measure of disorder or randomness in a system. It connects deeply with macrostates and microstates. A macrostate describes the large-scale properties we can observe, like temperature and pressure. In contrast, a microstate gives a detailed picture of where each particle is and how it moves. For every macrostate, there are countless microstates. Picture a gas in a container at a certain temperature and pressure. That macrostate can occur with many different arrangements of the gas molecules. Each arrangement is a microstate. The interesting part is that many microstates can lead to the same macrostate. Now, how does this relate to entropy? The more microstates that correspond to a macrostate, the higher the entropy. We can express this relationship mathematically using Boltzmann's formula. The formula states that entropy equals Boltzmann's constant multiplied by the natural logarithm of the number of microstates. This means that as the number of microstates increases, so does the entropy. In practical terms, entropy measures how much information we lose when we only describe a system by its macrostate and ignore the details of the microstates. When a system changes spontaneously, it typically moves from a macrostate with fewer microstates, which means lower entropy, to a macrostate with more microstates, indicating higher entropy. This behavior aligns with the second law of thermodynamics. For example, think about ice melting into water. The ice has a specific arrangement of molecules, representing a lower entropy state. When it melts, the molecules can move more freely, leading to a higher entropy state. This transition illustrates why many processes are irreversible or spontaneous. In essence, macrostates define entropy by grouping together all the microstates that create the same observable conditions. The greater the number of microstates for a macrostate, the higher the entropy, reflecting the system's disorder and the likelihood of that macrostate occurring. This connection is essential for understanding how systems behave and the direction of natural processes in thermodynamics.